Record. Hello, good morning, everyone. I'm glad to host Chris Oostenbrink from Vienna, Boku, the University of Natural Resources and Life Sciences. And Chris will be talking about molecular models of soil organic matter simulation meets experiment. Very exciting. Please, Chris, the floor is yours.
Thank you very much.
I'll just state, please turn off your microphones for the duration of the talk. And in the end, you can unmute yourself and ask questions. Go ahead.
Thank you very much for this invitation, and thank you for the introduction. Actually, it's a good point, I think, as an advantage of the current pandemic situation that we can more readily do these kind of presentations. So I'm very happy to share some of our work. And as you already said, what we'll talk about is mostly about simulation. So we are doing, I'm heading a group that is doing molecular modeling and simulation. And since a couple of years, we've been moving also towards the modeling of soil organic matter, mostly from a strong collaboration with the soil research group here at Boku. I would like to start with maybe just a reminder or an overview. Why does one do computer experiments at all? When are computer models actually useful? So simulations are there to replace or complement experiments. And there's different reasons why this would be useful. First of all, experiments might be impossible. If you're interested in the weather, then you cannot really do experiments with it. You can follow what happens, but you cannot try out what happens if I put a high pressure area here and a low pressure area there, and what will go on. So you can model based on observations and then get to a simulation. Experiments might also just be dangerous. If you want to make a plane, you want to make sure that it stays in the air. Experiments might be expensive. This is usually the first thing that students bring up if I ask, like, well, why do we do modeling at all? Because it's cheaper. Well, that could be, but it's not necessarily the main reason. A currently important reason is also that experiments might be just unethical. If you're interested in the global spread of a virus, you can do experiments with that, but you rather model it than see what goes on. But for us, the most important reason actually is that in a way, experiments are blind. And what I mean with that is that some properties you just cannot observe really what goes on, what really happens. And I highlight that in the next slide here. So in experiments, you're invariably looking at averages over very, very many molecules and on time scales that from a molecular point of view are very, very long. And I think this is particularly difficult in soil sciences, because we don't even know what these molecules might actually exactly be. And we have representations, we know what they contain, but it's not a very strictly defined molecule. So what you're measuring, if you are doing experiments on soil samples or on any kind of molecular sciences, actually, you're getting an average over very, very many molecules and long time scales. On the other hand, with simulations, we zoom in on individual molecules or individual individual processes, and we can do that on very, very short time scales. Or actually, we are limited to that. We're limited to small molecular systems and very short time scales. So basically, we try to address the same truth from two sides. Experiments give us an average over what happens when you consider many, many molecules at the same time, and simulations try to visualize and try to make clear what goes on the individual molecular level. So we're complementing methods to basically look at things. And then if you want to create a molecular model, then there's a few aspects that we need to consider. These four decisions basically always come back. The first one is the degrees of freedom. So what particles am I actually modeling? I can create models at many, many different resolutions as well. Am I looking at the finest, the chemically finest level? Do I have atoms that consists of nuclei with electrons around it? Or do I look just at atoms, or do I look at bigger supramolecular particles and see how they interact with each other? Yeah, that is all from the first choice if you create a model of your reality. given by that choice is also the next step is basically then already made, where you have to decide on how do I calculate interactions between those particles. These particles interact with each other, and that's what we somehow need to describe correctly in our models. This could be very simple interactions, just hard spheres, things that bump into each other, or they can be very elaborate models if you'd go for quantum chemistry, where you would really need to understand how the electrons move around your atoms, basically. And then a key issue is that we need to generate coordinates. What do our molecules actually look like? So in a computer model, we really do 3D modeling of our molecules. So we have every particle, every atom has X, Y, Z coordinates, and a molecule never stands still. A molecule is always can have different conformations, different shapes. So that's what we need to have a method to look at those different conformations in this very big variety of things. I now sell this a little bit easily, but it's actually behind this is the whole field of statistical mechanics, where you need basically you need to create ensembles of structures to be able to get averages that are comparable to the experimental findings. So that goes back to this observation that in an experiment we get an average over very many molecules. In our simulations, this means we need to consider very many different states, many different conformations of our molecules. And the last point of this slide is that we need to think about our boundary conditions. As I said, we can in a simulation intrinsically look at very, very small systems, nanometer scale. That means we need to decide how we treat the edges of this system because it's unrealistic. No one has a sample of just a few nanometers. So we need to think carefully about how these boundaries are built and how we do that. But also we have what we call thermodynamic boundary conditions. We can play with the temperature, we can play um, with the conditions under which we do a simulation. This is actually sometimes relatively easy to do in a simulation, not so easy to do in experiments. So I can easily heat up a simulation to a few hundred degrees Celsius and see how my molecules respond. Now, I would like to focus here on organic matter. So soil organic matter, this is what we will be looking at. And in the past, many people have created computer models of that should be representative of soil organic matter. So I just picked here one relatively random example where people tried to create a molecule that would be representative of a humic acid or a fulvic acid or whatever. Yeah. Now, there's a lot going on in this field anyway, so whether we should be looking at humic acids or fulvic acids or whatever is maybe a good question. But when we got into this, we said, well, our aim is rather not to look at an individual, to try and design one molecule that is representative of this plethora of different molecules that we have in reality, this whole big number, but we should rather try to make representative models. So we should create a classical condensed phase model, so something that is not just a single molecule in vacuum, but something that is as realistic as possible, water molecules around, there should be all kinds of things. And we try to create models of feasible molecules, not just one molecule, but many different molecules, and many of those, as many as we can of those molecules placed together in their interactions so that we can create that. So how did we do that? How did we start with this? We took these models that had been suggested before and we chopped them into pieces basically. So we collected a large set of molecules that had been suggested in the literature. We also took later on things from mass spectrometry data and things like that. But essentially, we chopped up all the molecules in smaller entities, and we call those entities building blocks. So we create a whole bunch of building blocks. Initially, we had 34 different building blocks, and then they can have different protonation states, so they can be protonated, deprotonated, etc. So we have a whole set of building blocks, and those building blocks we first then had to parameterize. This is a bit of a technical thing, but we had to then assign parameters to each of the atoms that tell us how these atoms interact with each other. So we chose to go by the Gromov force fields. I've been developing the Gromov force fields for almost 20 years now. Um, And what we created was these building blocks, and they all have a beginning and an end, an A and a B group, basically. And now now that we have all the smaller entities, we can construct bigger molecules again. So basically, we created them such that we can connect any A to any B. Yeah, so we can line them up again. So we can make bigger molecules out of these building blocks. And then I can, for instance, make molecules of about 5 building blocks, but I can make many, many different. This is now the combinatorial effect. I can make many different molecules because I have 34 times 34 times 34 times 34 if I want to create one of 5 building blocks. I have a huge amount of different molecules that I can create. And then, of course, I have to think at the ends how to patch these dangling bonds, but this is all can be done. So here's just an overview, basically. So now we have these building blocks. We have a whole bunch. We have a database. We created them from different sources. Most of them come from previously reported theoretical models. We have some that come from spectroscopic data, and some just come from our knowledge of what organic matter comes from, basically. So we needed something that looks a bit more like a lipid. We need something that looks a bit more like a carbohydrate, things that have peptidic bonds in it, like from proteins, from protein materials. All those functional groups that one would expect are in our set of building blocks. And then we need to put them together. So the next step is then that we try to put them together in a modeler. So what we have is a two-step tool, is an online and an offline step. We have an online tool, is a website where a user can specify now the measurable things of organic matter. So what I mean with that is we can measure from organic matter how many carboxylic acids are there, how many aromatics are there, how many hydroxyl groups are there. We can measure that from NMR or from spectroscopic techniques, basically. This is an input for our modeler. So we give as input the chemical composition that can be measured experimentally. And the modeler, then we also say how many molecules do we want, how wet should it be, how many water molecules do we want to add, do we want to add counter ions? And then what the modeler does is it creates a big set. Well, you specify how many, but a big set, think about 100 molecules. 100 random molecules that together fulfill as an average this experimental composition. And these molecules are first placed together at low density together, and then in an offline mode, we can condense them into a realistic model of our organic matter. I have this schematically here as well. So we have the soil organic matter modeler version 2 now. That's just in press, the description. It is online. So we have the VSOM modeler version 2. As a user, you put in the molecular weight of how big your molecules should be, the elemental composition, and you can also put in the organic composition. What I mean there is a distribution of functional groups. You can put in the pH that you want to simulate at and the water content and the counter ions. This then goes to a backend, to a modeler that creates then, based on these building blocks that we had, creates molecules, puts molecules together, assembles everything. And what the user sees is after some time, you get a model that is an output. And that could look something like this here already. So you see here lots of counter ions. The blue spheres are counter ions. These are, in this case, I think, sodium ions. And the green molecules are organic molecules, and they're packed together in very many, in a complex way already, as we think that organic matter in the end looks like, basically. It's many molecules. We don't know exactly what kind of molecules. There's lots of chemistry that has been going on, but we have a fairly random model. And we can create, so this is what it looks like. We can create different models. The output already gives you a first representation of your assembly, basically, of your molecule. It also gives you a report that one can download, download statistics. One can download how well does my model now represent the input that I gave it. And very importantly, I can download the files to actually run molecular simulations on these kind of models now. So the next steps are basically also already prepared. In the next step, in the offline step, what we do is we need to condense this system. So this first initial model is still a very low density model. It starts at the density of about I think 900 kilograms per cubic meter. And that's not realistic. There should not probably not always be huge vacuum bubbles in it. Maybe there are. There are. You can create your models at the density that you like. But typically you would want to create a higher dense model or a more dense model. And what we then do is we do a molecular simulation where we increase the, well, we have normal pressure on it, and due to the pressure, the system collapses and shrinks basically in time, in space, sorry. And over time, you can see then the density increasing. We have different ways of doing this. At different levels. The highest compact ones, we noticed it was useful to look at the energy of our system. So the interaction of all the amp molecules, and we can look at that over time. The systems with the lowest energy tend to have the highest density as well. And these values around 1500 are actually representative of experimental estimates of measurements of organic matter as well. Yeah? So this is a very realistic density that we get there. Let's not go into the details. So maybe it's good to just take a step back now before I start showing what we can do with the models, and think about what do we now get. So what we have now is a condensed phase model of organic molecules. Organic molecules that are overall, the whole sample is in agreement with the measured distribution of functional groups. Yeah, so I know that my molecules have the same amount of carboxylic acid, aromatics, etc., etc. These are really very small systems. So here's just a representation of it. This looks already very messy but I can zoom in on individual molecules. Here we see one of those molecules embedded in a whole set of other molecules, lots of waters around, etc. The overall boxes are typically of sizes of a couple of nanometers. 5 to 10 nanometers is a typical size of the boxes that we actually simulate. So it's really tiny, but we simulate them under what we call periodic boundary conditions. So that means if I have a box, if a particle moves out on one side, it comes in on the other side. So it's basically, it looks as if it's an infinite system. It looks as if it is an infinite lattice of these systems. So we don't have boundary effects due to the small sample size, but of course we have only a limited number of molecules that we try to represent this with. So if we think of the reality, we know, of course, that real soil is way more complex and more difficult. We have aggregates, we have all kinds of different kinds of materials that come together, and basically what we are zooming in on, this is a micro aggregate, and you see also areas of different composition and different elements. And what we are zooming in is really one tiny little piece of the organic matter. But we think that at this level is where relevant processes do actually take place. So absorption processes in the end are molecular processes. Things are going into the samples and on surfaces and whatever. Here we're looking at the organic matter mostly, but really at a nanoscopic scale. Yeah? So I don't want to claim that we're modeling soil. We're modeling tiny, tiny samples of organic matter. And then what do we do with it? We do molecular dynamics with this. So what we are doing, so now we have a static picture basically of it. So now we do molecular dynamics. What is that? We basically take snapshots of our molecules and we calculate the interactions between them. We calculate what the energy, the interaction between the molecules is. And based on that, we get a force on the atoms. We see where the atoms would like to move. Now, according to Newton, force is equal to acceleration, F equals m times a. So if I know the acceleration, I can also calculate how their velocities would change. And if I know their velocities, I can calculate how their positions would change. So I can deterministically predict what my system looks like if I have it at a time t, what it looks like at a time t plus delta t with a very tiny time step. This delta t is a very tiny time step. So I can predict where the atoms will move. I'm integrating Newton's equation of motion, typically with a time step of femtoseconds. And then we can simulate it. We can do this again and again and again. And because computers are faster and faster, we can do this a million or a billion times. And then we get simulations on the time scale of nanoseconds to microseconds. And at that time scale, we can already learn many things about the interactions of our molecules. For instance, we can start to look at properties of our sample. So here's now some first results. What I show here is as a function of the water content. So we ran a bunch of simulations of this is standard. This is a model that is representative of Leonardite humic acid as a model system. Yeah, we can make all kinds of different models. And we did them with different amounts of water embedded in the system. So we have a very dry system and we have relatively wet systems where we already get some phase separation and real water groups. And then we can look at, so we should focus here on the green lines. The gray ones are our previous version of the modeler. We had some issues with the packing, so the density was not so great. But we can look at the density as a function of the water content. We can look at this energy that is very central in the simulations, how strong the interactions are basically in my system. So drier systems interact more tightly. And we can look at other properties like a dielectric constant. Yeah, the dielectric constant is very important for how charged species interact with each other. So this is an interesting observation here. The dielectric constant of dry systems is very, very low, and the dielectric constant of wetter systems goes further up and up, as you would possibly expect. And we can also look back in our molecular interactions, of course. Now, if all the atoms are allowed to move around, if the particles are allowed to move around, then the question is, what kind of interactions do we actually observe? So here we have, for instance, calcium bridges. We had a system where we put calcium ions in, and we see that the calcium indeed starts to interact from different sides with the organic matter, and creates these kind of bridges between the different kinds of molecules and functional groups of the organic matter. If we have a system that is very wet, then you can also get water bridges. So we have many water molecules that also bridge between them, and the aromatic groups of the molecules, they cluster together. So you can follow the physics basically of your molecules. This is, of course, these are anecdotal pictures, but you can then also try to quantify that in terms of what we call preferential solvation. So these pictures here, they show, again, as a function of the water content, they show what species would like to be around the other species. So here we have organic matter, we have water, and we have calcium ions. And then if it's a positive number, basically, then here I have curves for the other species always. And then if it's positive, it means it likes to interact with it. So we see more interactions than you would expect just from a homogeneous mixture. So the organic matter at a high water content likes to be surrounded by water, but does not like to be surrounded by other some molecules so much. So the organic matter prefers to be actually solvated over being interacting with itself if there is enough water present. On the other hand, the calcium, and this I found a bit surprising myself, at high water content, the calcium really likes to talk to the carboxylic acids, the carboxylic groups of the organic matter, and doesn't like to interact as much with water anymore. Although water calcium interactions are very strong, that's why I was a little bit surprised about this. But this is an indication of this formation of these calcium bridges that I showed in the previous slide. So if it's possible, if things can move around, then the calcium would like to interact with the organic matter very much. But of course, these are now examples of Leonardite, but there's many different kinds of soils. And that's, of course, also the big problem. What are we actually looking at? So in order to address that, we started looking at a big set of different soils, and we took standard models that are available from the International Union of Soil Sciences. So they have different kinds of humic and fulvic acids. Even if you don't believe that humic acids and fulvic acids are relevant anymore, these are still useful samples that one can look at. So we can compare. We know they're experimentally characterized, and we can look at the simulations of them. And first we did based on their composition, on the chemical, on the measured composition. We did a principal component analysis, and then roughly could correlate. They make such a graph, which we could roughly correlate with. On the one axis, we get how much aromatic groups there are, and on the other axis, we have the acidity, so how many carboxylic acids are in these samples. So we have a nice spread over the both properties. We have different aromaticity and we have different acidity in our models here. And then for each of those, we created a large number of different models. I didn't emphasize that actually, but you can create, of course, with our modeler, we can create very many models that are all representative of a given sample. So you can actually do statistics over them as well then. So you can start to look at variations as well within the boundaries of the experimental observations. And then all these properties that we could look at that I just introduced basically for the Leonardite, we could now also look at for the different soil mass samples that we made. And here we then plot them again as a function. The most striking content things were the aromaticity and the carboxylic acids, so the number of carboxylic acids. And we see if we find correlations between these properties and the amount of carboxylic acids in the samples that we have. So if we have soils with very low carboxylic acids, they tend to go to a lower density than soils with a high amount of carboxylic acids. So now we are actually learning something from the data. We are learning we're trying to correlate the composition to the physical properties of our samples. This works, so we do see correlations with the carboxylic fractions. It turns out that basically we don't see any relevant correlations with with the amount of aromatic groups. So this is not a good correlation. But we see a correlation in terms of the density, again, in terms of the energy. And this also leads us already to a molecular interpretation of this as well. As we have more carboxylic acids, the ionic interactions get stronger. That leads to a lower overall energy in my system. And stronger interactions lead to higher densities, more strongly packed molecules. Yeah, so I can relate this together. We can also look at things that we can observe in our simulations that are not so easily observed actually in experiments. So the number of hydrogen bonds that we see between them. And here we monitor the number of hydrogen bonds between the soil organic matter and the water. And that seems to increase with the number of carboxylic acids. Yeah, more carboxylic acids, they are actually very strongly making hydrogen bonds with the water. So it makes sense that it goes up there. Accordingly, we also see that the number of hydrogen bonds between water molecules, this is now a normalized one with respect to the number of waters we have, but the number of interactions that the water molecules make with other water molecules goes down. And that's a very relevant thing because that means that the water is not as free to move around as you go to samples with higher carboxylic acid content. Again, aromaticity did not correlate with anything here. A very relevant but also difficult to capture property here is the diffusion of particles. So the diffusion of molecules through our simulation. This is something we can see. We look at dynamic processes. We look at dynamic simulations. So we can actually see what we can measure the diffusion. But because everything is very packed, this is also usually very low. So that the molecules don't move very, very much. What we do see is that the diffusion goes down with the number of carboxylic acids, especially of the water molecules. For the water molecules, we have most of them. We can most reliably also calculate the diffusions. The other ones, the correlations are not so strong, but in principle, things tend to get a little bit more stuck, which again makes sense. More carboxylic acids, stronger interactions, more packed. There's not as much moving around anymore. Yeah, so always in hindsight, you can always explain these things. Now we can also look at the interactions then of these molecules with other molecules or these samples with other molecules. And this is where we can get a stronger link possibly to experimental data as well. So what I do here is what I plot here is now I'm back to the Leonardite and I do here as a function of the water content. I look at the free energy of absorbing a water molecule in my sample, or the free energy of absorbing a methane molecule in my sample. Now, these are just models, of course. So I look at my water molecule as at this curve here. The green curve is a measure of the hydrophilicity of my model. If the water is very happy to go in, then the model is very hydrophilic. Yeah? If it's not very happy to get more water molecules in, it would be a more hydrophobic thing. The dashed line corresponds to placing a water molecule in bulk water. So if it's basically the same, if the green and the dashed line are basically the same, then a water molecule doesn't care whether it's in bulk water or whether it is in the soil. So it doesn't, there is no extra pool of water molecules into the soil model, into the organic matter model. The same here for the methane. If I have a very hydrophobic particle at very dry soils, it's very favorable to put in extra methane molecules. At higher water content, this approaches the amount of the free energy of inserting a methane in water, and it becomes unfavorable. Yeah, so it's positive value, so it doesn't want to go in there as more. A methane molecule would not want to go into this sample. So at dry samples, they are more hydrophobic, and wet samples are more hydrophilic because of the presence of these water molecules as well. But this also opens the way to do this for bigger molecules. So we don't just do it for water and methane, but we actually do this also for small organic molecules. So we look at, for instance, what we create is a thermodynamic cycle. So if we do that at the hand of an example here of phenol, what we would maybe be interested in is how phenol is absorbed into organic matter. Yeah, so this process of bringing a phenol molecule from vacuum into an organic sample. This is not so easy to calculate, but what is easier to calculate is actually disappearing them from each other. So we turn off the interactions. In a computer, we can do this. This is the strong point of simulations. We are the boss. We can turn off the interactions of the phenol in the organic matter, and we can do it in vacuum. We turn off the interactions, and we create a thermodynamic cycle. A particle that has no interactions has no free energy absorption because I can put it wherever I like. And that means that if I can calculate these horizontal arrows, I can actually calculate the absorption free energy as well. So we did this for a bunch of 20 organic molecules, different kinds, alcohols, ketones, aldehydes, some ring molecules, some molecules with rings, and they have a rest. And then we can correlate the experimental absorption-free energy on the x-axis with the calculated absorption-free energy from our models. And we did this in two different samples. We did it for very dry leonardite and for hydrated leonardite. And the ideal correlation, of course, would be the diagonal. There is a little bit of a shift here. This is a delta G because there is a constant value that is difficult to measure experimentally. But what you can see is that these correlations are actually reasonable. The black line gives the best correlation, and then with a Pearson correlation coefficient of about 0.75, that's a reasonably predictive model. So we can actually really predict there's no knowledge from the experiment going into this comparison here. So we can calculate these absorption-free energies, and we then can relate that to experimental predictions of where molecules would like to go. And that leads to that we can predict whether molecules absorb into organic matter or whether they stay in bulk water or where they would go. So this is actually a very important point of what we can do with these models, that we can also use this to make predictions, to make reasonable predictions. But of course, we can go bigger as well. So we've also been looking at interactions of organic matter with proteins. So some proteins are active in the soil environment, excreted by plants, fungi, bacteria. They do all kinds of things, also to be used in bioremediation. And in a very first attempt, we look at two very, very small model proteins with different properties, and then we simulated them in different models of organic matter. So we put them into our organic matter. And here we see a movie of that. I don't know how well this works with over Zoom, but what you see in blue is actually the protein. And in brown, you see our organic matter molecules. Basically, they start randomly placed in the box. And as the simulation continues, we see how they absorb onto the protein surface. And very important for us is the protein structure affected by this? Does the protein fall apart because of these interactions with these different kinds of molecules? Actually, they do not. So the proteins seemed very stable and don't change very significantly their shape. But then, of course, what we can look at is also the interactions of on the surface of the protein. So where do these organic matter molecules actually interact with the protein, and how does it do? The person who made this movie for me had no clue what he was looking at, so this is just some random orientations. Um, Anyway, so we can see that at the end, the protein is much more covered by the organic matter molecules. And then we can again try to quantify that. We can look at how do molecules, how do functional groups absorb around the surface of these proteins. And what is striking, we here did this for very different kinds of models. We did this for a protein in just a mixture of calcium chloride, of calcium acetate, calcium benzoate, more of a sum-like cis mixture of small molecules, but all really tiny small molecules, organic small molecules. And we did it with the protein with the different SOM models, with different sized models of our organic matter. And then what was striking, we did this for the two kinds of proteins, for Villin and for Spitz. What is striking, that basically the pattern is always the same. We get the blue peak, the green peak, the black peak. And what does that mean? We get first interactions with the carboxylic groups. This is a function of the distance from the surface of the protein. We first get the carboxylic groups, then we get the aromatic groups, and only then we get the calcium ions, basically. So we see how the interactions always go. And this is the same for all the kind of models that we created. So the proteins interact with this kind of preference thing. In the last couple of minutes, I would still like to say a few words about our efforts in also simulating minerals. Of course, mineral surfaces are also very important. Here we have a bit of an issue that simulations of layered systems become relatively can become artifacted. So we are distinguishing here two kinds of simulation. One where we have a periodic layer of a mineral with water in between, and one where we are treating it just as a slab, and their periodicity in this Z direction has been removed. That's a very technical story. I don't want to go too much into the details of that. What we're looking at here, first at the interaction of organic molecules on a kaolinite mineral surface. So we can see how they interact with each other. The molecule, the glyphosate molecule dances around basically. And we can monitor again what kind of interactions do we see, what kind of hydrogen bonds do we see, and what kind of interactions are there. What we can also do is we can calculate the potential of mean force. We can calculate the interaction energy of this glyphosate onto the mineral surface. So we get here, as a function of the distance from the surface, the free energy of absorbing a glyphosate molecule. We have a minimum energy. This is the position that it likes to bind to. And if you pull it away, the free energy goes up. And then we have two distinct cases. We have a neutral version of the glyphosate, so a completely neutral version, and we have the negatively charged glyphosate. And of course, the charged one binds much stronger. This goes further up in energy. The neutral one has a very low, a very shallow minimum of binding, I should say. And the charged one is much stronger. What we also see here is this is the difference between this periodic and the slab system. The black curve is representative of the periodic system, and this is possibly an artifact of the simulation, because it then, as I pull it away, it starts to see the next layer and the next layer and the next layer. So I have a continuous flow and a continuous rising free energy. In the slab system, it actually levels off to a constant value. And this is also what is still hampering a little bit our efforts now to put everything together. So now we have a layer of kaolinite and a probe of our organic material, and we look at whether they interact with each other. The space here in between is filled with water molecules that you actually don't see, because if I would show them, you wouldn't see anything. And what you can see here is that if we just simulate this, there is no, in the slab kind of model where there is no knowledge of the periodicity, there's not a very strong interaction yet. Maybe the simulations are too short still. We're looking at that. This is really very fresh still. If we are If we're doing it in a slab-like system, so where possibly there are some artifacts due to the periodicity, then we very quickly see that we basically separate the charges, and that's also the problem that I'm worried about. We separate the charges. The positively charged counter ions all go to the top of the system. The negatively charged organic molecules stay at the bottom of the system, and they start to cover the kaolinite. So we can actually start to look at the interactions of these molecules with each other and how organic matter um, covers the kaolinite surfaces. So this will be very interesting, because it will teach us whether it seems to spread out evenly. Basically, if we prolong the simulation a bit, I don't have a movie of that, it spreads out even further, or are the interactions of the organic matter with itself so strong that it actually rather stays as a blob and lies on the surface? So these are very interesting questions that we will try to address in the future as well. But this is really work in progress. Let me try to wrap up and give you some conclusions. So what we were looking at is mostly at computer models of soil organic matter. We don't try to replace experiments, but we hope that we can lead to insights of what goes on at a molecular level that is complementary to experiments. So we try to see how molecules interact with each other and what the effect of these interactions is on system properties that can be related to experimental findings. We can look at absorption, we can look at physical properties of the organic matter itself. So we want to really understand how the composition affects the macroscopic properties at a molecular level. I showed a couple of examples of accessible properties. So density, diffusion, hydrophobicity, we had the dielectric constant, we had various properties that one can look at, and also the sorption strength of small organic molecules. So we can look at how small molecules interact with this organic matter. And then we can go bigger, we can go to protein structures, we can go to mineral surfaces. That's basically the progress that we are going towards, the work that we are currently undertaking as well. With that, I come to an end. I would like to still acknowledge the people who actually did the work. So these are the current members of my group, and in bold are the people who did the work really. So Jerko Escalona is responsible for the VSOM2, the modeler itself, and for the simulations of different kinds of organic matter. Edgar Galizia is a postdoc who is doing great work on the mineral surfaces mostly, and the interaction with the organic matter, but also interactions with other molecules. Matthias Gottsmy was a very talented master student. He's still very talented master student in my group who did the interactions of the proteins with the organic matter. And Dražen Petrov is a postdoc who was doing the absorption free energy calculations. I work strongly together at BOKU with the groups of Martin Gerzebek and Daniel Tunega. And with a bunch of other people that are maybe not so much into the soil sciences. And then I would still need to acknowledge some funding agencies. And with that, I would like to mostly thank you now for your attention. And I'm very happy to answer any questions if there are any.
Thank you very much, Chris. If anybody has any questions, please unmute yourself and ask your question away.
This is Uri Mingelgren. Can I ask a question?
Yes, please.
Everything actually depends on the interaction potential between the different atoms or molecules. And you chose one model. Did you do sensitivity checks? Did you try to change the parameters of interactions and see how sensitive the results are to this change?
It's a very good point. So we use the Gromos force fields.
Yes.
And we did that for not just because I have been working with the Gromos force fields always, but because we also think that these are good, appropriate models. They have been parametrized against solvation free energies in hydrophilic and hydrophobic environments, which is exactly the balance that we need to strike here very well. So that's our argumentation why we started from these force fields to begin with. But we have looked also at modifications of it. So we have different flavors of the Gromos force fields as well. So we have there are different parameter sets, 54A7, 54A8, and we looked at the effects of changing these between these force fields. as well. The most important one there is actually the transition to the latest force field, where the parameters of the charged groups, which seem so relevant here, have changed. The overall properties of the organic matter are not very much affected by this, luckily. In more detail, we also did this for the models where we were looking at the sorption-free energy, so where the small organic molecules then interact with it. And there you, of course, need to be very careful that your models are appropriate. So there we tried a few more things, and indeed just the standard force. This is the standard parameters that we had, lead to a reasonable correlation that doesn't change very, very much. Where I'm still more worried myself is about the interaction between the minerals and the organic matter. That is a bigger challenge. The minerals we describe with the clay FF, the clay force field. That is parameterized against the same water model that we use in Gromos, but that's the only link that we really have. So there could very well be that we need to adjust parameters, or that we need to look at how strongly it depends on the parameters. Very good question.
Okay, thank you.
More questions, please.
It was very impressive. So everybody is under like a shock. You showed interaction with minerals, clay minerals. What about with microorganisms and roots? Do you try to simulate the mucigel around the roots?
Yeah. These are things that we have basically in our minds on the agenda, but there we should be aware of the fact that we have that we're really simulating these tiny systems. We are on a nanometer scale. So what does a root look like on a nanometer scale is then the question, of course. So what would the appropriate interaction partner be? Are those cellular systems then, or that would be then the questions. I'm quite confident that one can do these things, because many of the living material basically people have been making models and simulations of before, but you would need to have either membranes or glycosylation surfaces. Basically, you need to create appropriate models of that. And there, I fear a bit that the big diversity on the surfaces, on the scales, basically, or the big difference between the relevant scales for a root system and what we can simulate are going to be an additional challenge here.
Next question, please. Well, if everybody are still in shock and there are no further questions, I think probably you can contact Chris later on. I know Michael will probably have many questions after he watches this recording. And yeah, if Chris approves, we will also upload this video to our YouTube channel that is under construction.
Yes, you can.
Thank you very much.
No disasters have happened.
So thank you very much, Chris, for joining us.
Thank you.
You're very welcome.
Thank you.
It was a pleasure, and I hope I gave some insights into a new field.
It was very interesting.